Sure. Assalamu alaikum, everyone. The topic for today's tutorial is regression, and I will be discussing regression and its implementation in Python. To start with, just to give a little introduction about the difference between regression and classification. In classification, we are trying to predict, or we are trying to analyze, or we are the class variable of our problem is a discrete variable, is discrete in nature. Like if I want to predict the if a patient will survive or not, so it is a discrete variable with a value of 1 or 0. But in regression, we are trying to predict a continuous value. Like if I want to predict the sales for a company for the next quarter, so this is a type of a regression problem. And I cannot emphasize enough about the importance of regression uh, in real world also, and in this course also, because it is very much used in the industry. So there are some basic assumptions for regression model. Number one assumption should be, in case if we are doing a linear regression, so the relationship between our predictor and the predicting value, the class variable, should be linear. And the assumption the assumption can be used, can be tested using the scatter plots. The second assumption for the regression is that there should be little or no multicollinearity. This means that the multicollinearity assumption means that there's a relationship, there's a high positive correlationship or high negative correlationship between the independent variables. The variables which are used as an independent features shouldn't have a very high correlation between them, or else we would be facing the problem of multicollinearity, which means that our regression wouldn't able to give accurate results, or in case of high multicollinearity, our regression would be failed. The next assumption is the normality assumption, and normality assumption assumes that the errors which are generated from the regression follow the bell curve distribution, which is a normal Gaussian normal distribution. Uh, Another assumption is the constant variance assumption, which is known as the homoscedasticity. This simply means that the error which we are calculating from the regression should be constant, should have a mean of a constant. The mean variance of error should be a constant term. Another assumption is the conditional uncorrelated errors, which means that the covariance, that there should be the errors which are generated from regression shouldn't have any covariance between them. Their covariance should be 0. So we will be testing all these assumptions in this tutorial. And the last assumption is that there should be strict exogenous relationship between the regressors, which means that the error terms are random. This means that the mean in the error terms should be 0. Though this is known as the strict exogeneity of the regression. When these assumptions are satisfied, so we move with the regression. If one of these assumptions is creating an issue, so we should first correct that assumption, and then we should try to regress the problem we have with the relationships between the variables. If, for example, if I'm not having a constant variance in my error terms of a regression, so I should use different techniques. There are different techniques to correct the measurements of the regression, and then I should proceed with the regression. Okay, so to start with, I would be using the Boston dataset, and these are the libraries which you are already aware of. I would be using scikit-learn to import the dataset, and I have loaded the Boston dataset over here. So, so the Boston dataset has been loaded, and if I want to see the data set, so scikit-learn has already given has already have some data sets to some data sets to understand the concepts. So some basic data sets have been loaded in the library. So I'm using the Boston data set from there. So the load Boston command has been used, and I'm storing the data set in the variable Boston data set. Then next, the data set contains, this is a structure of a dictionary. So it is a, a Python structure for dictionary, and I want to see the keys of the data set. So there is a data, there are five things in our data, in Boston data set provided by scikit-learn. There we have a data, then we have a target variable, then we have feature names, and then we have a description of those names, and then we have file name. So one by one, I would be exploring those things, how to load in the pandas data frame. So if you see the feature names, if I pass the feature names in my Boston data set, I've passed the feature names in a square. I want to index the feature names because it's a dictionary. So I'm giving a key for the dictionary, which is feature names, and it would be giving me the values. So there's a relationship key and value, but you don't have to understand, go in much further detail about this. So the feature names gives us all the names of the features. There are around 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 features. So we have 13 features. These are independent variables in our data. And then when I called the features.decr, so this is a description. So I have directly copy and pasted all the descriptions of these variables over here. So we have per capita. What we are trying to predict. So we are trying to predict, in our case, the median value of owner occupied homes. So we want to predict the price of house, that what would be the price of the house, and this is the variable which would be dependent variable, and we would be using all these variables as our independent variables. So if I want to, for example, see the relationship between the the price and the per capita crime rate, so I would be using crime rate as an independent variable, and occupied homes, the prices of the homes as a dependent variables. And notice that all the prices are in thousands of dollars. So this would be very useful when we are trying to interpret our regression interpretations. Okay, now next thing is to load the data in our data frame. So we use pd.dataframe, the function given by pandas, and we pass the data set dot data. So here I am passing data set, Boston data set dot data. As I discussed before, that Boston data set has provided us five keys, and I am using this key for the time being. So I showed how to use this key, feature names, which has all the features, and the ECR, which has all the descriptions, and the file name. It is not useful for this tutorial to see the file name. So we would the data has been loaded here from using the Boston dataset dot data, and the columns I am giving for the data set is the Boston dataset dot feature names. So as I said that feature names, all the feature names, I want to make it a column header. So I am telling pandas to make the columns is equals to Boston dataset dot feature names. So what it would do, that when calling Boston dot head, so it would give the 5 top sample points. So as you can see, all the columns have been made as our feature names, and all the data has been loaded as a sample points. Okay. So but notice one thing, that there is we don't have any variable, our predictor variable, which is the prices of our house. So this is not part of our data frame, because Boston dataset dot data only contains the predictor variables but not the class variables. So we would have to we would have to access this value using the target variable. Okay, so seeing the shape of the data set, we can see that we have 506 rows and 13 columns. Now I would be using the target column, which is stored separately in Boston dataset. So in the scikit-learn, so they have separated the target variable with the class variable, but I want to merge both of them to get to get a better feel of my data. So now what I'm doing is that I'm introducing a new column in my data frame, in the Boston data frame, and the column name would be MEDV. This is the median price of the house, and I am accessing Boston data set which I've loaded over here, the Boston data set which I loaded over here, and I'm passing the target variable, the target key. So what it would do, that it would create a new column, and all the target variables would be in our column. It would be part of our data frame. So as we can see that MEDV now it is part of our data frame. Moving next, before doing any modeling, it is very good. It is a good practice to explore our data and to make some and to get an idea that what our data looks like. And to start with, we should always check with the null values. As you can see that this data set which I've picked doesn't contain any null values, so we can safely move to our next step. Okay. Okay. So the next step. Uh, So the next step, I want to plot the distribution plot of our MEDV column. The MEDV column is a predictor column. It is always good to see the distribution of how the data is distributed in MEDV in a class variable. So I have passed this as a distribution plot. This is SNS. SNS. Okay, ignore this for the timing because it's just to adjust the figure size how I want the figure to be. So I have passed this as a figure size. And, and the important command is this, the SNS.distribution plot. So Seaborn library, as I'm using over here, which I have loaded in the package. So I am passing Boston. The column name is MEDV. So what it would give us a nice distribution plot of our data. So as you can see that most of the data has been standard between the prices are between $10,000 to $30,000. So most of the data is between them, and we can see that there's approximately a normal distribution. So our curve is almost approximately normal, although we can see that we have a right tail distribution. Some of the data is also on the heavier side, like we can have outliers, as we can see that we have a outlier over here. Okay, so next we move to create a correlation matrix. So the correlation matrix tells us that the correlation between the variables, and to get an idea what the correlation matrix looks like, I am using again I'm using the library of Seaborn and matplotlib to make this correlation. Okay, how I have made this correlation, it looks like a very good plot compared to the pandas it gives. But important thing is to note that this diagram, this representation also gives us a scale. So if we have high correlation, so it instantaneously gives us a direction that these are the high correlation matrices and positive correlations. For the negative correlations, if we can see that so the negative correlations should be less than minus between 0 and -1, right? So the lighter values are less, most of the columns are being positive, and the high correlation are between the positive columns, as we can see that 0.74, and this is the high correlation. And how I've made this, I have made this using the boston.corr function. So I had Boston data set which was loaded. So .corr would return me the correlation from the data frame, and then I am rounding the correlation to 2 decimal places. So this is the .round function I am using, and then I have made the heat map. So this is more than a heat map. So the command used is the from the Seaborn library, and this is sns.heatmap, and I am passing my correlation matrix over here as a data, and I want to annotation is equals to true, which means that I want to annotate the values, the correlation values on my heat map. And these are just to adjust the figure that I want to make the figure size, and I want to make the columns and the rows. If you don't give these parameters, if you don't adjust the figure, then it would be a very small figure compared to this figure. It would be a very small figure which wouldn't be very useful to interpret. So I've just used to increase the width and increase the size of the matrix. Okay, so moving on, uh, what we saw from this correlation matrix, we can see that we have a very high correlation between RAD and TAX. So we should not use them together, as it will create the problem of multicollinearity. So as I mentioned earlier, that one of the assumption of regression is the multicollinearity problem, which means that if we are using two predictors at a time, two independent features at a time which have very high correlation, so our results wouldn't be very accurate. And sometimes if we have such high correlation, so our regression would fail. Sometimes we would get an error from the libraries which we are using, because the technical problem is that it wouldn't be able to compute the inverse of the matrix of the what we are in the regression. So again, it's a technical thing. So we shouldn't be using them together, these two variables, RAD and TAX. So what is RAD and TAX? We should go over here and see that RAD is the index of accessibility to the radial highways, that how close are the highways from the house. So the more close the highways, the more price of a house should be. And again, full property tax. So as the prices of the homes rises, so the property tax would also be positive. So these so these columns are positively correlated, highly positively correlated. Okay, and there are some columns that MADV has a negative correlation between them, so we can use them as a regression with them. Okay, if you want to find the average house prices with the rooms per dwelling, so rooms per dwelling is RM in our data. So I want to find the relationship that if the number of rooms increases, so should the prices of the house increases? By theory, by practical assumption, it says that yes, it increases, but by how much? I want to find how much. If we increase room by one, so how much dollars in dollars would my house price increase? So this is the type of problem I want to address. So this is the equation which we are trying to address. The average house price is equals to beta naught, which would be a constant term in our regression, and there's a beta 1 which we want to try to estimate. And these are rooms per dwelling. So RM, that the rooms per dwelling means that the number of rooms per house. Okay, so beta naught is the intercept term, and beta 1 is the population estimate for the rooms per dwelling, and we want to estimate these two values through the regression. Okay, okay, so next we try to find the values of these beta naught and beta 1, but I am using b as a small, because these are the population estimates and these are the sample estimates. So if you don't understand, it's just to give an idea that the population estimates are never true, but we try to find the population estimates using the samples. So this is a sample, right? We have a sample of our population of 514 samples of the population. It is not the whole population. So what we are trying to estimate is a sample. So for sample, we write the capital. We shouldn't write capital, but we should write the small b's. Okay, next I use the stats model API. So it is again a library in Python. So I am using stats models, and I have used as SM, as I've imported as SM. So now I want to build the I want to build the model. So I want to keep the dependent variable as average house price, and independent variable as number of rooms per dwelling. So according to this equation, this should be my dependent variable and this should be my independent variable, average rooms per dwelling. Okay, so how I am doing this, as you can see that in Y I am passing Boston and the column MEDV. So as you can see that MEDV is our last column of our data frame, and this contains the average house prices. And in X, I am storing Boston data of RM. RM indicates that RM is the rooms per dwelling. So I have stored my data in Y, X and Y, and now I have introduced a constant term over here. So for this API, we have to give that we also want a constant term. The constant term would mean that the if the rooms per dwellings are 0, so what would be the price of the house? So this is the constant term. If we won't add this constant term over here, so it wouldn't give us a beta naught. It would directly give us a beta 1 into rooms per dwelling. So it wouldn't be giving the prices of house for zero rooms. But for regression equation, we should be introducing a constant term over here always. Okay, now I am fitting my model. So I am using SM, which I have imported from the stats models, and I am using .ols. Now .ols is the ordinary least square estimates we want to find. The regression, there are a number of estimates when we run a regressions. So there are a number of estimates which we can use. There is a generalized least squares method. There's a ordinary least squares method. So there are a number of families. We say that the least square for least square estimates, but we want to use the OLS method. So we are passing sm.ols, which is taught, which is also used in the course, which is also used by Ms. Amin in K9, which is also used in K9 also. So sm.ols, and I am passing my dependent variable as y as my average house, and x is the average rooms per dwelling. And then I am using results. So I am fitting my model by using model.fit and model.fit, and I am storing the results in the results variable. So this model was created over here. So over here I should write model is created, and over here model is estimated. So over here we are now when we run this command, so our model is estimated. Now we want to see the summary of our result. The beautiful thing about this stats model is that it gives the regression results in a very compact way. The reason for choosing this library is because it gives us a number of regression results in a compact way in a table form. Else I could have used scikit-learn also, but the reason for using is I've mentioned. So when I pass the results.summary, so results.summary is a function which would give us a table like results in our data of our regression results. Okay, so it tells us that we are using MEDV as a dependent variable, we have used OLS as a model, and we have used least squares, and it gives us a time for my regression to run. So as you can see that I ran the regression today at 2 p.m. Around 2 p.m. and there are a number of observations, there are residuals. So all the information has been, and most importantly, it also gives us R squared. So 50%, around 48.4% variation is described by the variable rooms per dwelling. So this is how we interpret the R squared, not the adjusted R squared. We cannot interpret adjusted R squared. We can interpret the R squared, which says that the 48.4% variation in the model is described by the rooms per dwelling. So you should know the interpretation of all the things. Then there's a F stats. So F statistics is used how important how it tells us that the probability more oftenly we should be using the probability. So this is a F stats value, and when we see the F stats table, so we get the probability. So as we can see, the probability is very low, that is less than 5%. So it tells us that the model is significant, which means that the overall model which we have constructed over here is a significant in a statistical terms. Then there's a log likelihood, which are an AIC, BIC. There are other measures which I think at this stage you don't have to understand this. Okay, and then we have covariance type is also robust and non-robust. You shouldn't be going in these much details, but the important thing is this regression coefficients. So the interpretation of this regression coefficient is very much important to understand what has been happening over here. So remember I introduced the constant term over here when I made the model. So the constant term is giving a minus 34.67. I would be going in the interpretations, but for to just understand what is going on over here, you just have to go through and you just have to digest these results. So this is a standard error. So the standard error tells this is another name for standard deviation. Standard deviation for our coefficients. So constant is one of our coefficient, which is beta naught. So it is giving us a standard deviation of beta naught, that how much our beta naught, how much our constant would differ. And this is important, the t stats value. And more important is like we have a large t stats value. So large t stats value indicates that we would having a very small probability, and the small probability can be seen from here. So a small probability value tells us that our model is significant. Our coefficient is significant. So it is of good use to introduce this coefficient in our model. So this small p value indicates this. Again, for the RM, and these are the are which are known as the confidence interval, the 25% confidence interval and the 97.5 confidence interval. This mainly tells us most of our data would be ranging between minus 39.87 and 29 point, minus 29.46. Next, the RM coefficient. So the RM coefficient, this tells us that when we increase the number of house by 1 unit, so there's an increase of $9,000 in our in the prices of the house. So this is the interpretation of the RM coefficient. So if we increase the houses by one room, if we increase the room of an house by one room, so the value for which the house price would increase would be positive $9,000. So this is how we interpret the coefficient of this. There's again the standard error, which is just standard deviation, and again a large t stat value, which would indicate we would have a low probability, which indicates that yes, that the rooms are very significant to give us a relationship between the house prices and the number of rooms. And again we have got the uh, 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 confidence intervals for the for our coefficients. And these are number of other statistics which is not useful for our course, which is a foundations course, but they are used in finance. They are used also in the especially the DB Watson test is also used in econometrics. The JB test is also used in econometrics, but we shouldn't be using them over here. Okay, but if you are using in a reports, so you should report all of these stats as in this table form. So the JB test, just to go through the JB test tells us the normality, that if our errors are normally distributed or not. A high JB value indicates yes, that our errors are normally distributed, and this is the giving the probability. So again, a low JB value tells us that yes, the error normality assumption is satisfied. So I have already interpreted the coefficients, that the B naught is the average house price is negative $34,670 when number of rooms are zero. So since we know that the prices cannot be negative, so this estimate does not make sense over here. So this estimate is nonsensical, because we know that prices cannot be negative. But the important coefficient is this one. So when average number of rooms per dwelling increases by one room, so average house prices increases by $9,102. So I am converting this and multiplying it by thousands, because all the prices are in thousands of dollars. So this tells us that the positive relationship between the number of rooms and the house prices, which is also true. Now we need to see the assumption of the error terms. So by the results.resit, so the results .resit stores all the error term results. So now we want to see that whether our error terms does follow the normality assumption. So when we plot this, so I'm using plt.hist command, which is used as a matplotlib. Plt.hist command, and then I'm passing labels as residuals. So as you can see that we have passed labeled as residual, and I'm just telling it to show the plot. So as you can see that most of the it is almost like a normal is a normal graph, and it is pretty much following the normality. Again, the JB test is a statistical test which would give us a better picture of a normality. But seeing the figure, we can also get a better insight of the error normal or error normality. Okay, next I am plotting some plots. So as you can see that this was the regression MEDV, which was the house price predictions, and this is the RM, number of rooms, which are in discrete, and these are the MEDV prices, and this red line, as you can see, this is the fitted line, and as the blue lines, the blue scatters, which you can see are these data points. So as you can see that house prices are peaked, are capped at $50, $50,000. So no house price increases $50,000, and they may be considered as outliers over here, as you can see. But in regression, the outlier problem is not very significant until and unless we have very large values, and we can see that we have black lines. So these black lines are giving us a confidence interval of our point estimates. So as you can see that for this point which we have predicted, so this is the confidence interval, and for this point we can see that it is lying between -10 and positive 15. So the like this, it has given us a very nice result summary, or we can see the diagram of our fitted value and our data points. Okay, now I have plotted again the residuals with our RM, the rooms per dwelling. So as you can see that most of the residuals are following a pattern. So which means that our assumption of constant variance assumptions is not satisfied. So how to check the constant variance assumption is not, as the number of points increasing, so the variance of our data is also increasing. So we make a fan from here. So as you can see from my mouse that we as the number of uh, uh, as x increases, so y is also increasing. Okay, so so we need to correct this issue, and we are going for further analysis in this because it is violating this assumption. Okay, how I made this? So I am using graphics.plot regressor. This is a regress exog. This is I have borrowed from the SM library, stats model library, and this is how I am laying my figure. The important command is this, and I am passing RM. I want to see the fitted values of RM, which is number of rooms. So I've passed the number of rooms over here as a string, and it has given me a very nice plot. You don't have to understand these two values because this again is a concept for further courses in regressions. Okay, I interpreted the plots. So the black line is the confidence interval for each point estimate, as I told, and from second figure we can see from over here we can clearly see that errors are not random. So the errors should be random, and they seems to be dependent on rooms per dwelling. So as number of rooms increases, so the errors also have been increasing at the towards the end. So per dwelling, which is the violation of our constant variance assumption. Hence we have a problem of heteroscedasticity. Our errors should be normal. Our errors shouldn't be relating with the independent variable. So the constant variance assumption is violated over here, which says that it should be homoscedastic, which rather than heteroscedastic. Heteroscedastic means that there is a relationship between independent variable and a residual. So this should not be the case in our regression. So I hope you understand, I hope you got an understanding of regression, because it is a very much used tool in industry, where and most of the projects and many of the regression problems, many of the problems in data sciences, in econometrics, are being tested using regression. In finance also, most of the time we are performing regression. So a better understanding of regression would allow to apply most of the concepts, apply on the data sets, apply and to check the assumptions of what are the assumptions of our data, and are these assumptions being satisfied from from the regression. So I hope you get an understanding, and uh, this is all for the tutorial 11. And I hope there's one more tutorial, I think, which would be on PCA, principal component analysis, which would be conducted next week. So thank you very much. End the tutorial now. Allah Hafiz.